Hello, today we are going to review energy for AP Physics C. And what we're really looking at is just first of all how to set up energy, what's the basics. Then we're going to look at what are some sort of different kind of scenarios that are maybe a little bit simpler to solve but can be a little bit less intuitive. And then finally, we'll look at energy graphs, which are an important aspect to think about. So let's go ahead and jump right in. So remember our steps for energy, if we go back to our toolkit, is 1, EI equals EF. And so we're just saying, okay, we're using conservation of energy. That's why I'm writing that down. And then step 2, plug in types of energy. And then step 3 is just answer or solve, right? We gotta solve with units. And so we just kind of go ahead and find the answer. So this is not too bad. Something maybe like this. I have an H here, a ball, not a ball. A box is sliding down with no friction. And I want to know the V here. The initial velocity is 0. So all we need to do is EI equals EF. My initial velocity, I have potential energy. So PEG, potential energy from gravity. Plus I have no kinetic energy because the initial velocity is 0. The velocity at this point is 0. So this will equal, at the bottom, all this potential energy here is going to be gone. So I'll be left with just KE. Now you plug in your formula for PEG, which is mgh, and then plug in your formula for KE, which is 1/2 mv squared. You'll notice the m's cancel. In energy, the m's almost always cancel unless I have a spring involved. So go ahead and then just solve for v. So I have 2gh equals v squared, so root v equals root 2gh. The nice thing about energy is that the path, maybe it's kind of got some hills in there or something like that, the path doesn't matter. It's just the total change in height that actually matters for this scenario. So not too complicated. Hopefully that's something that you kind of have down pat pretty well. Let's go ahead and look at something that isn't too difficult, but it's something that definitely can trip people up. I feel like I see a lot of people messing up these types of questions on practice tests, and it's definitely something that we need to be able to get. And so it really says something maybe like find change. Let me go ahead and write that out. Change in KE. Okay, so let's say I have something, I have this car that's moving at v equals 10 meters per second. Has a mass of 100 kg, and then at some later time, now it's moving at 5 meters per second. The mass is still 100 kg. And it says find the change in KE. Now remember, if I have change in V, that just equals what minus what? Hopefully you remember that that's just VF minus VI. So exact same thing here. If I have the change in KE, then that is just KE F minus KEI. Okay, but this is a really important thing to do. I feel like I see a lot of people trying to do EI equals EF, and these types of questions where it's maybe find the change in KE, or it could also be something like find KEF divided by KEI, so the ratio of the final kinetic energy to the initial kinetic energy. Or something along those lines, or it could just be find the kinetic energy at a particular point. And they're trying to do this, where because I'm given sort of these velocities, I'm not solving for an individual velocity. I'm really trying to just plug in this formula. So I have delta KE equals 1/2 mv f squared minus 1/2 mvi squared. So delta KE equals, so 1/2 times 100 times 5 squared minus 1/2 100 times 10 squared. Okay, and then you solve this and get an answer. And since it's KE, I would have a final answer in joules. Shouldn't be too hard, but I just want to give you permission that it's not always EI equals EF. There are some scenarios where it's simply just KEF divided by KEI, or maybe just the change in KE is KEF minus KEI. And I think sometimes we just get confused, so just wanted to make sure you've seen that and kind of have an opportunity to know that that's okay sometimes to do that. If we know the velocities, then we're probably not doing an EI equals EF. Remember, if sort of basic energy, the idea is V is our unknown, is a pretty good clue that we are using EI equals EF, our conservation of energy. And so that's definitely something to think about. You should also remember that it could also be maybe solving for this initial height. That sometimes is a good clue to use energy. And then also remember that energy is a great go-to. So if you're really stuck, energy can be a great way to analyze something and get something going if you really have no idea how to approach a problem. Last thing I want to talk about is potential energy graphs. So usually we'll actually say U instead of PE, but those two things are just synonyms, so they are equal. And we'll have some kind of graph here. So maybe it's a straight line here, and then maybe something like this. And what these kind of graphs are always doing is they're saying, I'm going to start at a particular point. So these will be labeled. And then let's say I'm starting here, so dot, 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 dot. And let's say this is 3 meters. Okay, and then dot, 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 dot. This is, let's say, 10 joules. And maybe it says something like I'm starting from rest. And so in this scenario, what I will be using conservation of energy, most likely. And then what I need to do is I'll say, okay, I'm starting from rest, so I don't have any KE. So it'll just be, I'll put U. U equals, and then maybe it's, this is 6 meters, and then this is, let's say, 5 joules. Find the KE at 6 meters. So I have EI, I will still have U at the end, and then I'll also have KE. So then I just plug in, well, the amount of energy I have at the beginning is just this 10. So I plug in 10 for that, equals the potential energy at the next point, which is here. And so I'll plug in 5 here plus KE, and then I can just solve for KE. So KE will equal 5 joules. I could also solve specifically for the velocity if they give me the mass in this scenario. So let's say mass is 10, so then I have this. I would actually probably not write out that first. I would go ahead and go to the next step, 5 plus 1/2 mv squared. So go ahead and just plug it in here and solve through this conservation of energy type question. So then I have 5 by subtracting 5, and then I have 1/2 times 10 v squared. So multiply by 2. This cancels. I have 10 equals 10 v squared. Divide both sides by 10, and I have v squared equals 1, so v equals 1 meter per second. And so that would give me that final velocity, or that velocity at this 6 meter point. Alright, so here equals 6. A really important way, or sorry, not 6, 1. A really important way to visualize this is imagine I actually am putting a marble on this graph. And so obviously this thing will come up here, and the question is how far it will go. Well, it will go up to the same height of 10. So it will only go up here, and then it's going to oscillate back and forth forever unless there's some sort of slowing down force, like a friction or something like that, that would eventually cause us to end up at the equilibrium, which would be at this bottom point here, right, that bottom point. So these aren't necessarily too tricky, but it's definitely something that you kind of need to be familiar with. One other thing to think about for this type of question is to remember that the force is the slope. So for example, at this point here, the force is 0 because the slope is 0. Same thing for here, and then also for this tangent line here. Right, so at that bottom at 6 meters, the force would be 0. And then you actually see this on your, so that's an important thing to remember as well, that the force is the slope or the derivative of the potential energy curve. Okay, and so that's pretty much everything in energy. Hopefully that will help review you for the AP test. Thanks so much.